Great. Thank you. Are you able to hear me okay?
Sure. Yeah, it's good.
Great. Okay. Yeah, so today I'm going to be sharing some results of a project that has been going on for a couple of years called the EGS Collab project. I hope that you didn't get too much of this earlier today, and there's not too much overlap with the presentations of particularly Joe Morris and Pat Dobson, who are also involved with this project. And so I'll be focusing on the idea of underground laboratories as a tool to study hydraulic fracturing, and talk about some of the things that have been learned in past such laboratories and in this project. So I want to recognize this is a big multidisciplinary, multi-institution project. So the co-authors I've listed here are a small number of the larger list. And so I want to give acknowledgement to this is a work of a much broader team. So the outline of my talk is I'll first just talk very briefly about the history of underground laboratories in rock mechanics and hydraulic fracturing in particular, and the importance they've played in really developing our understanding of hydraulic fracturing. I'll then talk about a particular test bed that has been developed as part of this project called the EGS Collab project. And I'll focus in particular on our observations on fracture initiation and fracture propagation and kind of a longer term response of these fractures during a long-term thermal circulation test. So first, a little bit of history of underground laboratories, specifically as it relates to hydraulic fracturing. So I highlight here two previous projects that I think do deserve much credit for what we do know about hydraulic fracturing, which, although far from incomplete, there are quite a few things that we now understand fairly well. And these two projects, I think, played a big role in validating these understandings. So the first one is the one on the left. So this was a project led by Norm Morpinski in the late 1980s at the Nevada test site. So they did a series of hydraulic fracture tests from boreholes, and then were able to mine into and see what the fractures actually looked like. And so the photo you can see on the left is showing, in this case, the red stripes you can see on the rib of the mine drift there are the hydraulic fracture, and it's multiple stranded, which is interesting. But it shows that the fracture actually terminated where it encountered a higher stress zone. And so this, we all sort of take for granted now as something that is often looked for in petroleum reservoirs is a nice stress contrast between the reservoir and the overlying and underlying formations to contain the fracture in the reservoir. But this was not known at one time, or it was anticipated by models, but it wasn't known if it was really something that really occurred in practice. And this series of tests really showed that this is in fact what happens. And this same test also showed that things like Young's modulus and fracture toughness differences between zones have have really almost a negligible impact on the height growth. So from just borehole data on the surface, it would be difficult to draw these conclusions conclusively. On the right is a series of tests, as one of many tests conducted by Rob Jeffrey and his colleagues at CSIRO, where similarly they did hydraulic fractures and then mined into them in a variety of different environments, geologic environments. And so the sort of yellowish green strands you see there is the hydraulic fracture. So again, it's showing kind of multiple strands, and that it's a much more complex thing than many of our models anticipate. So that's a little bit of the history, and I think it's important to point out the invaluable insights that have been gained in the really ground truth understanding of the behavior of hydraulic fractures that can really only come from seeing them or coring through them, as we've seen in more recent tests. So I wanted to give that as a little background, and that I think we're trying to accomplish something similar in this EGS Collab project. And We're not actually mining into the fractures in this case, but we are working underground and in a way that allows us to make measurements and much closer, careful observations of the hydraulic fractures than is typically accessible from deep wells drilled from the surface. So a little bit of background on the project. Again, I hope this isn't too much overlap with the previous presentations. This is at the Sanford Underground Research Facility in Lead, South Dakota, in the Black Hills. It's a former Homestake gold mine, and the series of tests that I'll be talking about today were conducted on the 4850 level. So that means the nominal depth below ground surface is about 4,850 feet to the mine drift where we're working from. And then on the right is a schematic showing the drift, kind of showing this gray tube going, kind of to the upper right is the drift, the mine drift that we're working from. And then the green well is our injection well, the red well is the production well, and the other series of wells are monitoring wells. And so we have arrays of seismic instruments, electrical resistivity tomography instruments, fiber optic for distributed temperature, strain, and acoustic measurements. So it's a very well instrumented test bed. And so I'll talk now about our observations in specifically fracture initiation in these wells. So first, a little bit of background. So I guess one thing I forgot to mention on this slide is so these wells are all sort of sub-horizontal, and the injection and production wells are nominally in the direction of the minimum principal stress, so that we would expect fractures to form transverse to these wells and connect the injection and production well. All right, so a little bit of background about what seems like a fairly straightforward thing, creating a hydraulic fracture, but it's actually fairly complicated when a well is drilled in the direction of minimum principal stress, even though that's the most common thing that's done, in shale gas and is drilling wells, so such that you tend to get transverse fractures. But just to talk through the mechanics of this a little bit, if you look at this cartoon of a borehole that's pressurized, if the minimum principal stress direction is the sort of direction into the screen here, I didn't put up the Kirsch equations on the screen, but it's pretty intuitive that as you increase the pressure, the wellbore will stretch outward, and it will tend to decrease the magnitude of the hoop stress or the tangential stress to the borehole. But it actually has very, very small impact on the stress in the in plane or into the page direction here, which is actually the direction that we're hoping to cause the stress to decrease and eventually become tensile and generate a transverse fracture. So without some sort of defect in the borehole, there's really nothing to encourage a transverse fracture to develop at the borehole. Instead, if you increase the wellbore pressure enough, you're likely to split the wellbore and produce an axial fracture, which is not favorably oriented to propagate into the far field, since that's a maximum horizontal stress direction that it would be opening against. So the fracture will need to reorient in some way. And often what happens is, as shown in this figure on the bottom, which is an open hole fracturing in the Barnett Shale. This is an FMI log, where you can see both transverse and longitudinal fractures, so both formed. And the reason this matters is often the fracture in the near wellbore is very complicated because of this sort of competition between the near wellbore state of stress and the far field, and it creates a big hydraulic pressure loss that kind of impedes the production or injection, as the case may be. And so understanding this and being able to predict it and eventually control it is an important factor in working in horizontal wells. And all this also applies to cased and perforated wells to a bit different degree. It's a little bit different scenario. So I'll go through two examples of two different stimulations that we did in this test bed. So this zone is at nominally 42 meters measured depth into the injection well. And so what I've shown here is on the schematic on the left, we have a straddle packer arrangement so that the sort of dark gray, the top and bottom are packers, and then the zone in between them is what we're pressurizing. And because of the issue I mentioned on the previous slide, we actually machine notches, so a radial notch to try to promote formation of a transverse fracture. And on the right is the pressure versus time for the very early time when we were first initiating the fracture. And you can see that, you know, the pressure builds pretty much linearly with time until the pressure reaches about 23.5 MPa, and then it starts to bend downward from that linear trend, which is an indication of that a fracture has formed by that point. But you can see the pressure continues to build to 31 MPa, so quite a lot. So the breakdown pressure, which is the peak pressure here, is very, very large. And what the series of logs shown here, labeled ATV 1, 2, and 3, these are acoustic televiewer logs taken before the test on the left, and then 2 post-test measurements. And what you can see, hopefully, in the arrows that are showing where you can see fractures that were induced. So they're present in the post-test, but not in the pre-test log. And the fractures are not transverse, and they're not quite longitudinal. They're a series of kind of en echelon fractures. And so this is what often happens in these horizontal wells. And so this explains why we have such a high breakdown pressure, because the fracture near the wellbore is not opening against the minimum principal stress. It's opening against a larger combination of the minimum and some of the larger principal stresses. And so this fracture, we ended up not doing our circulation test in this zone because the treating pressures were so high. It was an indication that things were not quite what we wanted, and the pressures required to circulate here were very high. So a large hydraulic impedance. So this is at a different zone in the well at a little bit deeper depth, nominally 49 meters. And so again, you can see these notches. And if you look at the pressure versus time curve here, you'll see that the pressure, the fracture begins to open at about the same pressure, so 23.8 MPa here. And it doesn't rise significantly above that. And in fact, it begins to decline, which is more the behavior you'd expect of kind of a radial hydraulic fracture. And so this fracture, I guess looking at the image logs here, you'll see that there's almost no difference between ATV 1 and 2, which ATV 2 was taken shortly after the fracture was first initiated. And that we can't be sure but it likely indicates a fracture initiated from the notch. And we don't have these sort of longitudinal or en echelon fractures, which is consistent with the much lower breakdown pressure. And so this is ultimately the test, or the stimulated zone that we chose to do a long-term circulation test and ultimately drive the fracture to the production well. And then we injected cold water to do a long-term test, and I'll talk about that test later. We did notice, so ATV3 was taken after the long-term test, and you can see these axial fractures that are actually underneath the packers. And as I'll show later, the pressures during the long-term circulation test were much higher than the 23 MPa shown here. And so those are responsible for those longitudinal fractures. So this slide shows when we actually drove the fracture to the production well. So I'll start with the left, and then I'll show this video. So the red is the pump rate. So we started off doing the step rate test at a controlled pressure, and then eventually switched over to a constant rate test and pumped as high as 5 liters per minute. So, and then the pressure is shown in this dark blue color. And shown in the bottom 3 plots are the microseismic events that we detected and their distance from the injection point. And so the north, south, east, west, and up, down directions are the 3 plots, top to bottom there. And the vertical dashed gray line is when we first saw that the fracture intersected a monitoring well that was in between the injection and production well. And then the vertical dashed orange line is when we first saw indication that the fracture had reached the production well. And so I'll show this video, which is kind of cool. And the first part of it isn't, it'll take a minute to get to the really interesting point. So I'll explain. This is during this test shown on the left, we actually drained all the water from the production hole and put this camera down in the well. And this is us then sweeping the camera up because we were looking to see where the fracture actually intersected. And so you can start to see some like wisps of, it looks like smoke, but it's actually water vapor from what's now behind the camera where the water is flowing into the well. And so you'll see in just a moment as we move, the camera moves a little further up the well, you'll actually see some jets of water squirting into the wellbore, which is where the hydraulic fracture, and I really should say hydraulic fractures, because as you'll see, it's not just one fracture, it's a series of multiple fractures that intersect not far from one another. And so this was a really exciting moment for us because, you know, as I mentioned earlier, this is the sort of thing that you often, well, you pretty much never get to do in a large, deep well, but in this intermediate scale underground test bed, it's this sort of direct observation that we're allowed to make. So you can see the jets of water out of the top of the well now squirting in. So there's one. Now you can see another one squirting from the bottom, and that one you can see is actually coming from a natural fracture, which is the light colored stripe on the borehole. So just let this play. There's another set of inflow points a little further up. So that's at about 129 feet measured depth. The depth is shown in the upper left. Skip ahead a little bit. There we go. 127 feet. Skip ahead a little bit. Yep. So here's some more at 127 feet, mostly from the top. And so consistent with, you know, some of these observations you saw in the mine backs that I showed on the first slide, where the hydraulic fracture was really a set of closely spaced hydraulic fractures. So that's consistent with what we're seeing here. So I'll go ahead and skip to the next slide in the interest of time. But I should mention that this video is actually on, it's called the Geothermal Data Repository, or GDR. If you Google that, you'll be able to find this video as well as others. So I'll skip now to the longer term performance of the system. So we connected these fractures together, and then we circulated, you know, the test bed here, it's nominally at 30 degrees Fahrenheit. This is 30 degrees Celsius. This is a geothermal project. And so in order to create a thermal gradient, we injected water that was about 6 degrees Celsius. And we conducted the test for a period of many months. So first, I'll just talk very briefly about some of the mechanics of hydraulic fracture and how what we're doing here may differ from some of the conventional wisdom and the actual physics that occur in other disciplines. So when you inject fluid into a fracture, you know, a portion of the fluid is stored inside the fracture. It's taking up the volume inside the fracture. And then a portion of that will leak off into the formation. And what I've shown here is the formula for the fluid velocity that's leaking off into the formation. This is a Carter leak-off law. And so generally this is like a 1D diffusion equation, so that the velocity of the fluid leaking off into the formation decreases or is proportional to the inverse square root of time. And so tau here is the moment in time when that little patch of fracture first formed. So that each patch of fracture nominally would take fluid, but the amount of fluid it takes would decrease over time. But the leak-off area, if you're propagating a fracture, is also growing with time. And so there's this competition between each little patch of fracture is taking less and less fluid over time. But as you're generating more and more fractures, the fracture gets larger and larger. There's more and more surface area. And so, for details, I'll refer you to this very good paper, kind of looking at the scaling and dimensional analysis of this. But basically, this is a phase space of dimensionless parameters describing what physics are most important at any given time in a fracture. And generally speaking, the moving from left to right on this phase diagram is making the increasing viscosity decreasing importance. So it's important on the left, less important on the right. And moving from bottom to top, it's the leak off is of increasing importance. And what this shows is looking at a traditional fracture propagation model. Eventually, all fractures end up in a leak off dominated phase. And that's because the area growth, basically you're adding more and more area, and that's consuming more and more volume of the fluid. But the situation we're in here, where we've intersected a production well and we're circulating through this, we are at least trying not to continue to propagate the fracture. So the fracture is kind of static in size with time, but it's still inflated. And so we don't get that term of increasing surface area over time, but we do get this term of decreasing leak off from each area, unit area of the fracture versus time. And this is a regime of fracture behavior that's not really been studied nearly as much as the fracture propagation regime, because it's just simply not encountered in a lot of the oil and gas applications that are of more interest to the hydraulic fracturing community. And so the fracture, as I mentioned on the previous slide, the wisdom of hydraulic fracturing is eventually they become leak off dominated if you inject for long enough. But in this case, that would not be the case because we're not continuously generating new area. But one thing that becomes important here, if you're sitting there leaking off fluid over time, is you're building up pressure, additional pore pressure in the formation around you, which is increasing the total stress and therefore the stress that the fluid is acting against to keep the fracture open. And so this ends up in a phase where the fracture transitions back to a storage dominated, where most of the fluid you're injecting is stored in the fracture and less is leaked off. And the interaction with the poroelastic effect becomes more and more important. And so a little bit of evidence on the poroelastic effect. So this is the reopening pressure at this zone at several different times. So the first injection on May 22nd is the dashed blue line. That's the curve I showed before. So you can see now in PSI, I apologize for the switching in units, about 3,500 PSI was the peak breakdown pressure there. The next day on May 23rd, when we opened it, is the solid blue line. And so you can see we don't have the peak because it's just a reopening. So it reopened around 3,000 PSI. And then after we had circulated for a period of time in February of 2019, you can see the fracture doesn't begin to open obviously on this curve until 3,500 PSI. And then the flowing pressure after we've injected only a liter, so this is still very short term, is all the way, almost 4,500 PSI in February 26th. So we're seeing effectively an increase in stress over time that we can't say for sure, but we believe is due to a poroelastic effect, so an increase in the pore pressure. And a little bit more evidence to support this. So this is a curve that Peng-Cheng Fu, who I think will be presenting later, assembled of all of the test data on long-term injection. So on the upper curve, the blue line is the pressure, injection pressure. The green is the injection rate. So you can see we had some interruptions for equipment malfunctions and maintenance over time. But generally, the pressure over time increased from, as I mentioned, about 3,000, 3,500 PSI. So at the end of the injection in spring of 2020, shown at the far right, we were well over 5,000 PSI injection pressure. And to support this idea of decreased leak off over time, on the lower plot, this gray curve is the total recovered fluid rate over time. And we were injecting at 400 milliliters per minute for most of this test. So you can see it starts out the recovery, this is in liters per minute. So on the left, we were recovering, somewhere around 275 milliliters per minute. And over time, that gradually crept up. And at the end of the test, we were recovering almost the full amount, almost 400 milliliters per minute. And so that's speaking to this decrease in leak off over time and increase in injection pressure versus time. Okay, so I'll wrap up now with some conclusions and we can take questions. So our test has shown, along with many in the literature, that initiating transverse fractures from an open hole is difficult and often leads to significant tortuosity near the wellbore. So this wellbore geometry, it's become dominant in petroleum because it offers such a large access to the reservoir with many transverse fractures, but it comes with these near wellbore problems that even with the notches we created remain problematic in some cases. Despite the low porosity and permeability, poroelastic effects that seem to be well over 1,000 psi were seen over the course of just the period of months that we were injecting. So in this case, this is I didn't mention, it's a very low permeability porosity phyllite formation we're in. I suspect that the porosity that's giving us this poroelastic effect is actually fracture porosity rather than a matrix porosity, but we're not certain about that. It seems likely. So in this case, I'd call this a hydroprop fracture. We kept the fracture open by fluid pressure over time rather than using proppant or something like that. And so under this scenario, fractures are likely to extend over time since, as we saw, the fractures are needing the pressure required to open the fracture at a constant rate over time is continually increasing. But this poroelastic effect would be expected to some degree, even in a propped fracture, if you're circulating through it at high pressure over time. And so what that would look like is the increased closure pressure over time, which could, even in a prop fracture, result in loss of fracture conductivity. So those are areas that I think we're going to need to look at more carefully in the future that we've identified from this test. So I'll go ahead and stop there. Here's some references that I mentioned in the paper, as well as a much longer list of all the collaborators on this project, many of whom you've either heard from today or will hear from later today. And I think I'll stop there and welcome any questions you might have.
Okay. Thank you, Dr. Burghardt. So right now, I would like to read the question to you. So the first one is, how can we numerically implementing the multi-scale propagation behavior like viscosity, toughness, leak-off, and the transition ranging in fraction model?
Yeah, that's a good and not a simple question to answer. I'd say that there are many researchers who've been looking at the numerical side of fracture propagation. And I guess I'm not sure exactly what you mean by multi-scale, unless if you're talking about the. Sorry, the multiple strands of fractures. Is that what is meaning?
I think it means the fracture propagation in different regions, like sometimes in viscosity region, sometimes in toughness dominator region, and sometimes it's leak-off dominator region, as you show in the diagram. So, and sometimes in the transition region. So, how can we numerically implementing this kind of the multiple scale propagating behaviors in our fracturing model? So is that clear for you, Dr. Burghardt?
Yeah. Thanks. So yeah, I'm not as much of an expert in the numerical side of things. So I think I would encourage you to ask Peng-Cheng Fu later this afternoon, who's much more expert in that area. But I will just say that, like, all of these, if you have a model that incorporates leak off, viscosity, toughness of the rock, then these different fracturing regimes should occur in your model. Where you run into problems is when if you're using an analytic solution, for example, that neglects leak off or neglects viscosity and assumes pressure is constant in a fracture, then that model would only really work in one of these regimes that it was whose assumptions are consistent with that regime. But a fully coupled numerical model should be able to transition between these regimes, is I guess what I would say. Yeah.
Yes, thank you. So the next question is from Dr. Ali Zuizi from UH, the postdoctor. So on slide 9, how far is the injection wheel from the operation wheel?
Yeah, good
Slide
question.
9.
So this is it's nominally 10 meters. You go back there, or slide nah. I meant 4. Oh yeah, I see. Yeah, so it's nominally 10 meters. And so you can see we do see microseismic events. So I've drawn lines here, extend, north-south direction, which is actually so this fracture is nominally propagating east to west, and so you can see we see events as far away as 21, almost 22 meters to the west, and 50 meters to the east. Now, of course, there's probably some location errors there, but yeah, hopefully that answers your question. And you can see the vertical growth is actually quite symmetric. It's about 24 meters on either side, upward and downward, that we see the microseismic events.
Okay, so Dr. Ali just follow his question. The time that hit occurs. Not hit.
I'm sorry. Can you say that again?
Follow up the question about the time that hit occurs. A hit.
Yeah, I'm sorry. I'm not understanding the question.
Maybe I can. So my question was, how long after injection that hit occurs?
So you can see it's right here on the plot. So we start injecting, and so this is all in UTC time, just after 3 o'clock. And of course, we're in varying the injection rate over time. So it was. So I mean, you can see it here. I have to do the math here.
Half an hour, probably. Yeah, close to
Yeah.
half an hour.
Yeah.
For a time like 10-meter distance.
Yeah.
Okay. Thank you.
Yeah, but yeah, you can see we're injecting the first part of this injection. We were kind of holding things under a constant pressure and not really injecting a lot of fluid into the formation. But yeah, and just like with the video, all this data is actually publicly available on the geothermal data repository if you want to look at it and plot it. And love to see if anyone has a fracture propagation model and they want to try to model this. That would be great. Although some of my colleagues have done that. It's our desire to make this open and allow anyone to look at it.
Yeah, we have another question in the chat from Ibrahim. So, can we see the pore elastic effect on fracture injection test for estimating the closure stress?
Yeah, I think I understand this question. So the
pore elastic,
yeah. I guess the slide I showed with the reopening pressures, I would say shows this to some degree. I'm aware that reopening pressures are far from a perfect diagnostic. We did do some shut-in tests and look for closure pressure on the decline curves, but those we actually intentionally really limited the amount of fluid that we injected before we did those tests so as not to sort of pollute the stress measurement. And we did not, well, I would just say like repeating those tests is actually difficult in this case because interpreting a closure stress curve is traditionally done with analytic solutions that assume you're just leaking off fluid using a Carter leak-off law. But in this case, we intersected multiple other wells and we're losing fluid through those wells. And so to actually try to pick a closure stress during shut-in tests from after we've intersected the other wells is You'd need to use a numerical model and some sort of iterative scheme to do that, and we've not done that. So I hope I'm answering the question that was intended in saying that.
Okay, it's all for